Okay, we are back to naming in lesson 20. In this chapter, we're really going to look a lot at aldehydes and ketones and some more stuff with the carboxyl group. So first we need to know how to name them like we did before. Well, in naming aldehydes, we remove the E from the carbon chain and replace it with an al. And this isn't like all oil, like ol. This is al, al. So, let's see, we've got 1, 2, 3, 4, 5, 6 carbons in that chain. With an aldehyde, you would still number from the one containing the C-double-O bond. And so this would be number 1, 2, 3. That makes it 3-methyl hexan al. Note that there is also a hydrogen here, and sometimes that's drawn and sometimes it's not. So either way it would be the same thing. If you have 2 aldehydes, so on the ends, that would be a dial. So in this case we actually don't remove the E from the carbon chain. This becomes 1, 2, 3 carbons, therefore it's propane dial. Sounds like dial, right? But it's actually dial. And this guy always trips me up, so I'm sure that, it's not exactly easy to remember. This becomes, from the IUPAC definition of how to name this, it would be benzene, referring to this guy, carbaldehyde. And what that carbaldehyde is doing is it's saying, hey, there's a carbon right there that's involved in an aldehyde. I know, but that's the way we do it. That's the way the IUPAC does it. Truthfully, most of us have forgotten that after some time. Naming ketones. So here we're going to replace the E in the carbon chain with a one, O-N-E, because a ketone, get it? C-double-O gets the lowest possible number that it possibly can. So in this case, it doesn't really matter, but this would be cyclohexanone. But if you had another substituent, say right here, the C-double-O bond is the one that takes the number 1 in that numbering chain, okay? So that would be 1 and then 2, and then if you had something down here, that would be 3, right? Okay. Again, you want the C-double-O bond to get the lowest number possible, so you would start with the numbering here. 1, 2, 3, 4, 5. So that would make this 3-chloro, 2-pentanone. This is actually an enone, because you've got a double bond here, and you've got a C-double-O bond right there. So let's name the carbon chain, which would be 1, 2, 3, 4, 5. So it's actually pentan, right? Because you've got the E in there telling you that you've got the double bond. So this would be 3-pentan, 2-one. And if you really want to get technical, this would be trans. Pentan, 2-one. Good. Now let's say you've got a mixture of all kinds of crazy put in the same molecule. Well, what we do is we name sort of the ketones, ester, amide, aldehydes. That is going to be sort of your higher priority. So that's what's going to end up being the end of the word. So that means that we've got to then name the extra C-double-O bond as an oxo group. Not oxa, oxo. Okay? So this, basically, if we remove that guy, that's an amide, right? Well, it's an amide with a carbon 1, number 1 right there. So it would be 2-oxo butanamide. This one's tricky. It's not a dial. It's actually an aldehyde with a ketone in there, which means that we've got to name this one as a substituent. So if you were to remove that, it would be butanal. with the number 1 right here. 1, 2, 3 butanol, or 3-oxobutanol, excuse me. This looks like all kinds of crazy though, right? Okay, well, let's remove this first. Remember, this becomes our substituent. So that's isopropyl. We've then got a hexane here, but since this is an ester, we name it O8. So, isopropyl hexanoate. But in this case, we have a substituent, so it becomes 3-oxohexanoate. This, we're done with naming for a little bit now. Remember, the C-double-O bond is still sp2, it's still flat. If you have this guy reacting, and you start pulling electrons away from that carbon right there, it's going to increase its reactivity, because basically it's reactive because it is slightly positively charged. If you start having R groups that are pushing electrons towards that that carbon right there, then it's not going to be as reactive. Furthermore, if you have R groups that are big, huge, massive things down here, you can't have a nucleophile go into the center as easily, and it's going to be less reactive. Let me make sure I've got, yeah. Okay. Aldehydes and ketones do not undergo addition elimination like we saw in the last chapter. They actually only add, except for the ones that eliminate. So, yeah, welcome to not always. Nucleophile comes in, and it's basically going to attack right in here, and electrons go up, right? Just like we sort of had before. But in this case, when you add your acid, it just basically makes that an OH. Unless, if one of those nucleophiles has a lone pair of electrons available, those lone pairs of electrons that are available will allow it to sort of come up. So, let's say that we have an OH, it reacts with another acid molecule. You end up getting an OH2 that's a great leaving group. Nucleophile can then come in, that can come out, and you can end up with this type of situation. We'll talk about that more in a little bit. So this is just a general schematic. We'll go through the specifics a little bit later. Now let's switch topics for a little bit, because the first thing that we're going to use as a nucleophile is a Grignard reagent. And Grignard reagents are the ones that we sort of probably touched in class about, that are the ones where you're tapping, remember? And we talked about that in a previous video as well. And what you're doing is you're trying to get the sort of the oxidation off of that magnesium to start the reaction. This is a very water sensitive reaction, but you basically take a bromide, alkyl bromide, and you put it in magnesium and ether, put it with magnesium in ether, I should say, and that gives you this type of structure, which basically is pulling, this is sort of like, we've got a partial negative charge here on this bromine. The magnesium is a metal, so it's really partially positive, which makes this guy down here very partially negative. And so that bond can rather break and be sort of a really good nucleophile towards a carboxyl group. And these work beautifully. We have that come up and that come up, and you basically make first a salt. Then once you acidify it, bam, you end up with a really cool reaction where you just added an R group to a carbon. And that's a new carbon-carbon bond. Remember how hard those are to make. Carbon-carbon bonds are special, unique, and we love them. So you'll see this quite often. What's really cool to me, at least, is if you use CO2, just bubble CO2, through one of these Grignard reagents that you make, you actually just make a carboxylic acid. You make a carboxylic acid out of an alkyl bromide, which is awesome. Okay. Now, when you have an ester or an acyl chloride, these guys react not just once with a Grignard reagent, but twice. First they give you one R group, and that's replacing either here or here. But now you've got another ketone, and the ketone can undergo the same thing that we had before, and you end up with two R groups that are the same, that have been added to the same carbon. So here's the mechanism for that. Electrons go in and up. And just like we sort of had before with the ester, this comes out, that goes out. and there's your aldehyde, which can then react a second time. Electrons go up, you make an sort of a salt type of thing, and then once your acid comes in, it drives that off and you end up with an alcohol. So both of these R groups right here are from the Grignard reagent right there. So you have to make sure that you make enough, because it's really hard to stop it once you've got one going. Okay, and that's it for lesson 20. 10 lessons left to go. Or 9. Maybe 9. We'll see. Thank you. Bye-bye.